Hey guys, this is Mr. Perry. I thought I'd go through the honors radioactive decay activity. I felt the instructions were a bit lax. I don't know, I felt like they were kind of confusing. They could have been more clear. So I'm going to help you out with this one. Here's where you download the worksheet, and I'll pull that worksheet up for you. Purpose of this activity is to model the concept of half-life using a sample to represent radioactive atoms. For their sample, they say they want 200 M&M candies. Obviously, you don't have 200 candies just lying around, right? I imagine. Well, I guess Halloween was last month. Maybe you do. I don't. So we're going to use this little simulator. It basically just generates coins, like a penny, and then it does a coin flip. And so that's what we're going to use to represent radioactive decay. It says in the procedure, we're going to place 200 candies in the shoebox, lettered side up, cover the box. And, oh, God, can you imagine how meticulous you'd have to be? Like, that's so tedious. Like every single one going through and making sure it's face up. No, thank you. Anyway, you're supposed to shake the box, remove the lid, and then take out any candies that are showing lettered sides down, and that would represent atoms that have decayed, carbon atoms that have decayed. What we're going to do is we're going to use these pennies for the same idea, and basically any pennies that have gone tails up instead of heads up, we're going to consider those decayed, and we'll take them out. So let's start with 200, right? So of our 200 coins, 96 of them are heads up and 104 are tails up. So what I'm going to do is I'm going to put 96 here and 104 here. And this represents that there are 96 atoms remaining, carbon atoms, and of the original 200, 104 of them have decayed. And we're going to basically keep doing that. We're going to keep repeating this until this number gets to 0. So we have 96 atoms remaining, right? So I'm going to type in 96, and we're going to see how many of them decay. And I think it's after a 3-second period. There are 57 coins that are heads up and 39 coins that are tails up. Okay. Wait, what did it say? 57 and 39? All right. 57 and 39. Okay, so we're going to put 57 in here, 23 and 34. 23 and 34. And we're just going to keep doing that. Now there's 23 left, so now we have 9 and 14. Now we're going to put 9 here. Now we have 4 and 5. Put 4 here, 2 and 2. And again, your numbers might look a little bit different, right? Because this is all based off probability. So, it's highly, highly improbable that you'll get the exact same numbers that I do. Oh, 0 and 2. Okay, so we're done here. Your table might be a little bit longer. Some go up to 30. I don't think you have to go past 30. And you're going to do this a second time, it looks like. You're going to do it twice. I'll do that again. I'll skip over it, but I will do it again. Okay, I've done it a second time. So now we have our 2 trials. And you'll see it's relatively similar. There are some variances here and there. But what we're going to do now is it says determine the average number of atoms remaining, or not decayed, at each 3-second time interval by adding the results from the 2 trials and dividing by 2. So what we're going to do is we're going to take this number and this number, right, 96 and 97. We're going to add that up and then divide by 2, okay? So let's see, 96 plus 97 is like 190. Let me get a calculator, hold on. 96 plus 97 is 193. We're going to divide that by 2. I get 96.5. So what I'm going to do is I'm going to come over here and I'm going to write 96.5. I'm going to do the same thing at the 6-second interval. I'm going to do 57 plus 55 divided by 2. So 57 plus 55 is 112, divided by 2 is 56. So I'll come down here, and I'll write 56. And then we're going to go on to the 9-second interval. We're going to do 23 plus 28 equals 51, divided by 2 is 25.5. All right, and I'm going to keep going here. I'm going to do the 12-second interval. 9 plus 14 divided by 2 is 11.5. All right, let's go to our 15-second interval. 4 plus 6 is 10, divided by 2 is 5. I didn't need to put that in a calculator, but whatever. All right, so I'll put a 5 down. Our 18-second interval. 2 plus 1 is 3. 3 divided by 2 is 1.5. And then at 21 seconds, I think I had 0 for both. So 0 plus 0 divided by 2 is 0. All right, so there is my average atoms remaining. Okay, this is where it gets sort of weird. It says they want you to create a line graph of your data showing the average atoms remaining versus time. So we have that right here. What we're gonna do is we're gonna take this data right here and we're gonna put it into this graph that they already give you. Okay, and here's how you're gonna do that. It's a little bit weird. You're gonna right click and it says chart object. If you type edit here, if you look here, when you click edit, it sort of opens up this like Excel sort of looking format. If you look at this sheet, like there's chart 1 and sheet 1, what you're gonna do is you're gonna replace this data with the data that you have. So like instead of 175, mine is 96.5. And then it looks like it's 56. And then it's 25.5. And then it's 11.5. And then it's 5. And then it's 1.5. And then at 21 seconds, it's 0. And then everything is just 0 from there. Okay? So that's my information. Again, your information is going to look different, right? You could have some numbers here. It's okay if you do. And now we're going to see how that looks on the chart. And you see how that changes? Yours should look a little bit like this. And you might have different numbers, but you should see this general pattern. Okay, so let's look at these conclusion questions here. It says, after how many time intervals or shakes did one half of your atoms decay? Mine was pretty easy, right? Because it was only one time interval, so we're literally just going to put 1. It says, what is the half-life of your substance? Well, literally all you would do is multiply your time interval by 3, because that is our time interval, or intervals of 3 seconds. Our math is going to be super, super easy here, because, well, 1 times 3 is just going to be 3, right? So our half-life is 3. 3 seconds. All right, if the half-life model decayed perfectly, how many atoms would be remaining? When they say perfectly, they just mean, whereas we took an average, if we were to look at this perfectly, that would mean that in every interval, it would decay by exactly half. So for instance, instead of 96.5, if this decayed perfectly, that would be 100, okay? And then this would be 50, and then this would be 25, and this is, what's that, 12.5, I want to say? Math hard. All right, and then you do 12.5 divided by 2, which is like 6 point something, 6.25, okay? Oh, but we can stop at 12, can't we? Because it says, if the half-life of your model decayed perfectly, how many atoms would be remaining after 12 seconds? So pretty much all of you will have that answer. Assuming that you did this in like assuming that your half-life is 3 seconds. If it were maybe 6 seconds, then that would be a little bit different. Okay, if you increase the initial number of atoms to 300, would the overall shape of the graph be altered? I'm going to say no, right? Because this is a pattern that you should see in every half-life graph. It doesn't matter if this is 200 or 2 million, right? Well, we should always see this basic pattern. I will say the more you have, the better your data pool. But no, it wouldn't. And go ahead and explain your answer. You can figure this one out on your own, right? You can explain your answer going into the lesson and learning that. Go back to your data table, and for each 3-second interval, divide the number of candies decayed by the number of previously remaining, and multiply by 100. Show your work. Okay, so this question is really weird, the way it's formatted, but we'll do as they ask. Go back to your data table, and for each 3-second interval, divide the number of candies decayed by the number previously remaining. So, okay, so let's look at the 3-second interval here. So what we're going to do is we're going to take this number 104, and again, your number might be different. We're going to divide it by the previous number of remaining atoms, right? It did say remaining, right? Yeah, previously remaining. So we're going to do 104 divided by 200. And then we're going to multiply that by 100, I think it wants us to do, right? 100, yeah. Okay, so we'll do that. And we get 52. So I guess, I don't know, I guess we'll put this here. 3 seconds equals 52. 6 seconds. I guess we can just put an S there. Don't really need to. Equals, what does 6 seconds equal here? Let's see, at 6 seconds, we're going to do 39. Right, 39 divided by 96 times 100. And we get about 40.6. All right. And then at 9 seconds, we're going to do 34 divided by 57 times 100. Get about 59.6. "12 seconds, 14 divided by 23 times 100. Oops. Okay, so that's basically what you do. I know that sounds weird, but that is how you're going to do it. You're just going to look at the time interval you have. You're going to do, the atoms decayed, and then you're going to divide it by the previous number of remaining atoms. So it'd be 104 divided by 200 times 100. Then this would be 39 divided by 96 times 100. Then it'd be 34 divided by 57 times 100, 14 divided by 23 times 100, 5 divided by 9 times 100, 2 divided by 4 times 100, yada, yada, yada. And basically what they're trying to show you is that this number should be around 50%. Obviously, mine is sort of an average of 50%, right? Like here it's 52, here it's 40, 59, 60. If you added these up and average them, you should get around 50-ish. And basically, it's going to say, did this activity perfectly model the concept of half-life? Well, these numbers should have all been 50. If this was perfect, these numbers would all be 50. So obviously, it did not, and that's where you're going to put it. It didn't. It did not perfectly model the concept of half-life. I'd say it was relatively close, though. And then let's see here. Compare how well this activity modeled the half-life of a radioactive element. Did the activity model half-life better over the first 12 seconds or during the last 12 seconds of the experiment? If you see any difference in the effectiveness of this half-life model over time, what do you think is the reason for it? For this question, what I would have you do is just look at the graph. Like, what's more noticeable, this side of the graph or this side of the graph? Because this side, I can really see these changes. It's very obvious, but the smaller our number gets, the smaller our sample size. You see how it's just like, it's a lot harder to tell the difference over on this side than it is on this side. So I would say that it's the first 12 seconds that model half-life better than the last 12 seconds. Because the last 12 seconds, we got to 0 at like 18, so it's not like we really got to even see much change. But again, you can always see more with more numbers, right? So yeah, it would be the first 12 seconds. Anyway, that's how you do this lab. I know it's a little bit confusing, I think especially right here, these questions. But that's how you do it. If you have any questions about this assignment, please don't hesitate to shoot me a text if this was not satisfying for you, and I will happily help. All right, I'll see you guys later. Bye.